Welcome back to Matrix Analysis of Structures. Hopefully you're all staying warm. Today we're going to have a virtual lecture talking about finite element interpolation functions, a particular choice of basis functions that we'll see as being especially useful for solving boundary value problems through this whole approximate weak form and Galerkin type of method. So before we dive into that, let's do a brief recap to see how exactly we got to where we are now. So if you remember, we started the class talking about solving boundary value problems, which we'd set up by making some key assumptions about the physical behavior of some idealized structures in one dimension, where we might have some end loads and some distributed loads and boundary, support conditions and things that we can impose on a structure. We idealized the physics of these problems, nominally treating them as these homogenized or continuous media, assuming that we're restricting attention to physical behaviors. We impose some other constraints like the assumptions of linear elastic material behavior and also small deformations. So there's a lot of simplifications that went into idealizing the physics and turning it into an equivalent mathematical problem or a boundary value problem, which we expressed in one of two different ways. We could express it through the strong formulation of the problem, which was a statement of some governing differential equation, a statement of equilibrium that had to be satisfied in a pointwise sense at every location x along the length of this one-dimensional structure of interest. We tried to solve some of these boundary value problems, and in some cases it was easy to do. But in general, we find that trying to adapt that same solution procedure to more complicated structures that maybe include nonlinearity or two-dimensional problems or three-dimensional problems, that kind of approach that we took to solving these strong formulation types of boundary value problems just didn't work for us. So we actually manipulated our strong formulation into an equivalent weak formulation, nonetheless an equivalent statement of the same boundary value problem, and it involved defining this funny virtual displacement function or a test function that we plugged into these integral expressions that was essentially a statement of virtual work. The total external virtual work done on the structure by the external loads moving through this virtual displacement field had to be balanced by the internal virtual work done by the internal forces in the structure moving through some virtual deformation or virtual strain field. And that had to be, satisfied for any possible choice of this virtual displacement function. Now, the problem with these approaches, both the strong formulation and the weak formulation, they were posed in either this pointwise sense that it had to be satisfied at an infinite number of points x along the length, which made the problem really hard to solve. It was kind of intractable because there was an infinite number of points that we had to satisfy equilibrium at. But the same problem actually exists with the weak formulation. Technically speaking, our equilibrium equation, as expressed through this statement of virtual work, had to be satisfied for any possible choice of virtual displacement function. So that too essentially constitutes an infinite collection of equilibrium equations that we have to satisfy. So, somehow we had to simplify the problem and isolate attention only to particular virtual displacements of relevant interest to solving these problems. And we also had to kind of limit our possible choices for what we thought the actual solution field, the displacement field, looked like. So we chose a limited set of possible functions to represent both our displacement field and our virtual displacement field through something called a Galerkin approximation method. And that essentially amounted to representing both of these two different fields, the displacement field and the virtual displacement field, in terms of some finite collection of functions multiplied by some corresponding function coefficients, maybe u bar sub j or v bar sub I. And essentially, we reduce the problem down to parameterizing our solution field in terms of this set of finite coefficients, where in this case, maybe we have n total of these basis functions, the v's sub j's, and n of these corresponding function coefficients, multiplying them. So that was kind of the idea. We kind of discretized the problem or limited our choices for how we represent both of these two solution fields in terms of this finite set of basis functions with corresponding coefficients. And then once we had that, we could go about solving our problem, our now discretized boundary value problem. by taking our weak formulation of equilibrium and plugging in these different statements for these kind of discrete representations of these two solution fields. So plugging in these two different discrete representations for u of x and v of x into our weak formulation of equilibrium, we could make some substitutions. We went through some of the arguments in detail in the previous lecture, so I won't kind of go into the same details here, but just, to present some of the basics, we plug in these different representations for u and v, make some manipulations, rearrange some of these equations, make some arguments that for any arbitrary choice of these virtual displacement coefficients, the v bar sub i's, we rationalize that basically what we would get is a set of equilibrium equations, n in total, corresponding to each of these n different virtual displacement coefficients, whose arbitrary variation leads to the requirement that this kind of residual force equation or equilibrium equations, these had to be satisfied for all possible values of I ranging from 1 to n. So a total of n equilibrium equations, which we could use to solve for these n corresponding unknown displacement coefficients, parameterizing the unknown solution field. Okay, now making a few extra modifications. If we wanted to, we could re-express these different quantities that appear in the preceding expression, which we defined as the stiffness matrix, indexed in terms of these kind of sub-indices, a row index I and a column index J, or also in terms of our external force vector involving kind of these various quantities, external forces and distributed forces multiplied by corresponding basis functions. That was also indexed by I, essentially the row index in this particular vector. But essentially, we could take all those different quantities expressed in the previous expression and format them into this system of equations involving the stiffness matrix and some external force vector. And we could solve the system of equations for the corresponding vector of unknown displacement field coefficients, the u bar sub i's, where I ranges from 1 to n. So in compact notation, I'll kind of denote matrices in terms of this uppercase, boldface, capital K. The displacement coefficients I'll represent in terms of this boldface lowercase u, and then the external force vector is this boldface F external. All right, and we could invert this system of equations or invert the stiffness matrix to solve directly for u. We said we're going to reserve the details of how we do that for another lecture, but suffice it to say we can do this and solve for those corresponding coefficients. Okay, so that's all how we got here and basically everything that we've covered up to now in this class, just to kind of catch you up. Now the question becomes, we've said we can pose this Galerkin type of method and suppose that we can represent our solution fields u and v in terms of some finite number of basis functions, the phi sub i's. But the question really is, at this point, we haven't really been particular about what this set of functions should be. We've said in general that we can represent the solution in terms of some finite collection of functions, but we haven't been specific about what functions. And that's really the question that we're going to dive into in today's lecture. And just to recap what we covered in the previous lecture, we supposed in that particular example that we considered that the solution could be represented in terms of monomial functions, basically. So x squared, x cubed, x to the fourth, and so on. And it turns out that the monomial basis, as it's called, which is really just the collection of these kind of single-term polynomial expressions, multiplied individually by these different, corresponding coefficients for each monomial term, that actually constitutes a reasonable basis in some cases for representing certain classes of functions. It was particularly well suited for the problems that we were solving in the last lecture, but actually it turns out that monomial functions don't necessarily have some nice properties that we'd like to exploit. Sometimes it can be difficult to enforce certain boundary conditions also. At least in the last lecture, it was easy to do because we had just one boundary condition at this support. But enforcing boundary conditions poses a challenge in general if we're trying to use monomial-based functions. We could choose a different polynomial basis, and in some sense, we'll see that the functions that we'll choose at the end of the day will actually be kind of like a form of polynomial basis, but kind of restricted in terms of their domains of interest. All right, so that's one particular choice. We could choose to represent our solution field in terms of just monomial functions and corresponding function coefficients for each of those monomial terms. Another choice of basis that you could choose to represent some function with is the so-called Fourier basis, which is essentially just a collection of sine waves of variable frequency. And it turns out that there's some interesting mathematical proofs that you can show that any possible function that you want to represent, or at least a continuous function, can be theoretically represented in terms of some kind of infinite series expansion of either the monomial basis functions or the Fourier basis functions. So they both constitute good choices for approximating the representation of functions in terms of maybe some infinite series of these different terms, monomial terms or Fourier basis function terms. It turns out that, again, for similar reasons that the monomial basis wasn't a great choice for enforcing boundary conditions and doing other things, the Fourier basis is also not necessarily well suited to the types of problems that we seek to solve, at least in structural analysis types of problems. So there is another set of basis functions that we're going to go with that actually has some really nice properties we'll summarize at the end of this lecture. But they are the so-called finite element basis functions. And they are, in very brief terms, a form of interpolation for representing the solution, these function coefficients, in terms of not just arbitrary coefficients that don't necessarily have physical meaning, but in the case of finite element basis functions, these function coefficients, these u sub i's, actually represent the discrete values of a given function at particular locations of interest distributed along the length of the solution domain. So that's a nice property of these finite element basis functions. And they also constitute an interpolation. These basis functions allow you to represent the solution as basically being equal to these different discrete values at these discrete locations of interest. And in between each of these discrete locations, we interpolate the solution field in a simple way such that we assume that maybe in this case, the solution varies linearly between these two discrete values where we're specifying these corresponding coefficients. So that's the finite element basis for choosing to represent some solution as essentially a piecewise linear function. So relatively simplistic. And you can kind of see that the form of these functions, we'll go into the details, looks kind of funny. It looks like these kind of triangular functions that have a limited range over which they're non-zero. Okay, so first, before we dive into some of the specifics of how we define these functions, I want to provide some preliminary terminology regarding the notion of finite elements in general. You might have heard this terminology. We alluded to it briefly at the start of the class, and we said that finite elements were really a kind of a particular case or, are very closely related to the subject of matrix structural analysis and in particular, the direct stiffness method as it arises in structural analysis. But I want to provide some more precise definition of what I mean by finite elements. And a finite element method really comprises both a discretization procedure as well as the solution procedure for some of these structural analysis problems. So suppose, just for the sake of example and defining some of these terms relevant to finite elements, suppose I had some domain of interest ranging from x equals 0 to x equals L. A finite element method proceeds by essentially discretizing this domain into a collection of elements, which themselves are terminated by so-called nodes. And nodes are really just a finite collection of points that we might distribute along the length of the structure. So I might have, in this example, 5 nodes, which are really just 5 points that I've placed along the structure. I'll call those x1, x2, x3 through x5. So these are the nodes, or if you like, you can think of them as joints or discrete points, but really nodes are the terminology used in the context of finite elements. So we define these nodes, and in between each of these nodes, we define elements. So an element is really nothing more than a finite subregion of this structure as a whole that is terminated by its 2 nodes that bound that subdomain. So elements 1 through 4 are bounded by nodes 1 and 2, 2 and 3, 3 and 4, 4 and 5. All right, so that's what we mean by an element. An element is really just a subdomain that's kind of described as being the interval between 2 nodes. Okay, then once we have these elements, we assume something about how the solution varies internal to a given element. So suppose I looked at element 1, and in element 1, I can define discrete values of the solution as belonging to each of the nodes. So at nodes 1 and 2, maybe I define discrete values, u1 and u2, for the displacement at nodes 1 and 2. And I define as many of these displacement unknown values at each of these nodes. So for this problem, I have 5 different values, discrete values of the displacement defined at each of these nodes. And local to element 1, I can say something about how the solution varies within this element. And if I know that at node 1, I have a displacement value of u1, at node 2, I have a displacement value of u2, then within this element, I assume a simple form of interpolation that just linearly ramps up the displacement from u1 to u2. Very simple. And I can do this individually within each of these different elements. So in element 2, I linearly interpolate the values of u2 and u3, the values of the displacement at nodes 2 and 3 that terminate element 2, and so forth. And essentially, I form this piecewise representation of the solution field that is dependent only on the nodes that terminate a given element. So that's the simplest explanation I can give for how these piecewise functions are defined on an element-by-element basis based on the corresponding nodal values of the solution field being interpolated within that element. Okay, so we're talking about piecewise functions. That's essentially what these finite element basis functions are, but they're interpolatory piecewise functions defined in terms of function coefficients that directly correspond to the value of the function of interest defined at each of these discrete nodal positions. Okay, so the question now is, how do we define these interpolatory functions for a given element where maybe we have two nodal coordinates, x1 and x2, where we have defined these two solution coefficients, u1 and u2. And the question is, how do we come up with some interpolatory function over this element that passes through these two different values, u1 and u2, and which kind of varies in a simplified way in between those two values over this element? So we have these two conditions. We want some function, which I'll call u of x, that satisfies these two constraints, that u evaluated at x1 should give us back u1, and u evaluated at x2 should give us u2 within this particular element. And if I have essentially two values for the solution that I seek, u1 and u2, and essentially two equations that enforce these two conditions. You could think of them kind of like boundary conditions, but they're constraints on what this solution for the interpolatory function should look like. I can relate these two different equations to two corresponding coefficients in some assumed polynomial interpolation of these two values. So the simplest function I can think of that passes through these two points is a linear function, and I can parameterize that linear function in terms of a constant term a and a linear term b. So I have to solve for a and b, satisfying these two equations. So two equations, two unknowns. I can set up a system of equations to try to solve for both of those two different unknown coefficients, a and b. And in general, I can do this by saying, take this form for u of x, our assumed linear interpolation function, and try to satisfy these two equations. So plug in, x1 and x2 into these two equations and enforce the conditions that u at x1 should be u1, u at x2 should be u2. And now I can actually rearrange this, if I like, into the format of a matrix and a vector, or kind of a system of equations that I can set up and solve for these unknown coefficients a and b. That's just kind of an aside. Obviously, you could also just directly solve these equations. In the case of solving this system of equations, it turns out that I should arrive at values for a and b that look like so. And if I plug those two different solution values for a and b back into my expression for u of x, I'll get an expression that looks kind of like this. So u1 plus the difference, u2 minus u1 divided by x2 minus x1, and then multiplied by x minus x1. So an interpolatory function that passes through u1 and u2. And I'll encourage you to go through the exercise, verify that when you plug in x1 into this expression, you'll get back u1. When you plug in x2, you'll get back u2. Okay, very simple linear interpolation. And you could do this for 2 nodes. You could do this for 3 nodes, where maybe there's an extra node in the middle here. And you're trying to ensure that some function passes through all the different nodal values of these displacements defined at these discrete nodal positions. So a few different ways that you can construct these interpolatory functions. This is probably the simplest one, linear interpolation. All right, so we've come up with this form for U that interpolates the displacement expressed in terms of the axial coordinate x ranging from x1 to x2. But in fact, this is a somewhat uncommon way of representing how this function varies internal to a specific element. If all we really care about is representing the solution in this interpolatory way over a given element, then in practice, it's actually more convenient to express things in terms of an element's local coordinate system, which is essentially a coordinate system that ranges between 0 and some normalized coordinate, which I'll just say is maybe equal to 1. So we actually want to take this domain, which technically ranges x between x1 and x2, and convert it or transform it into a different domain that ranges from 0 to 1. So a normalized coordinate domain or the element's local coordinate system. And we can define this local coordinate over a given element through this funny Greek symbol called xi. It's sort of like this calligraphic squiggly E, if you like. And really, that transformation ends up being rather simple. We can basically just shift our coordinate frame by x1 to get us down to 0, and then we can normalize or divide by the length of this interval. So divide by x2 minus x1 to get the range to be defined from 0 to 1. So that's kind of the simplest way that we can make this substitution by defining this element local coordinate system as starting from 0 and going up to 1. And if we do this, we can basically say, maybe do some transformations and instead represent this function as ranging from the element's local coordinate xi equals 0 up to xi equals 1. All right, if I make these substitutions, I basically can transform our representation for this function expressed in terms of x. I can rewrite this expression in terms of xi. And what I'll end up with is something that looks a little bit different. I'll have essentially this expression. U as a function of xi equals u1 plus the difference u2 minus u1 and then multiplied by xi. So a relatively simplified expression. Looks a little bit less complicated than this expression in particular. So that's kind of one nice point about this. But I can actually manipulate this expression a little bit further. What I'd like is to actually factor out u1 and u2 into two different terms that multiply maybe two different functions or kind of expressions that I've kind of denoted in these different colors here. So u1 ends up multiplying 1 minus xi, and u2 ends up multiplying just xi. Now, if I like, I can recognize the fact that this particular expression, u as a function of the element's local coordinate xi, is expressed as some function coefficient u1 times a given function, 1 minus xi, plus another function coefficient multiplied by a different function. And it turns out that these two functions and these two coefficients constitute a particular choice of basis functions local to this particular element of interest. And defined in such a way that, it doesn't matter exactly, where the element starts or how long the element is. It's defined generically for some element that has a normalized coordinate ranging from 0 to 1. So that's the nice thing of defining things in this kind of generic, one-dimensional normalized unit domain, is I can define these functions for any possible kind of choice of coordinate system. So I now have our function represented in terms of some coefficient u1 times the basis function n1 plus u2 times the second basis function. And these two basis functions actually have a special name in the context of finite elements. These are the so-called finite element shape functions, which are nothing more than the basis functions isolated to the particular element of interest and expressed in terms of the element's local coordinate system, xi. So these basis functions, when you plot them over the element's local coordinate frame, look kind of like this. n1 has a value of 1 at xi equals 0, and then slopes downward with a constant slope down to a value of 0 at xi equals 1. And n2 does the opposite. It's 0 at xi equals 0 and 1 at xi equals 1. So you can verify that just kind of looking at the form of these two functions. But these local, basis functions or these shape functions essentially give us a way of representing the solution over this particular domain of interest. And you can relate this back to how we were choosing to represent some function as the summation of some function coefficients, each multiplied by corresponding basis function, so that we've kind of rearranged things into this format. So n1 and n2 are local basis functions or our shape functions. And we can define these basis functions in a piecewise fashion over the entire domain by stitching together these shape functions taken from each individual element of interest. So in element 1, I have basis functions n1 and n2 represented local to that element and in terms of that element's local coordinate frame. And they look the same for each one of these different elements, but they're associated with different nodes that are scattered across the domain. So if I wanted to take these functions and piece them together to construct the basis functions defined over the full domain of interest for the problem, from x equals 0 to x equals L, I have to take these shape functions and basically pattern them together to form the actual basis functions for each individual node in this case. So I have as many of these basis functions as I have corresponding nodes where I have the solution values u1, u2, u3 defined. And if I take a look at maybe just one of these basis functions, let's say n3, this is, I guess I should say, not a basis function or rather not a shape function anymore. This is the basis function associated with node 3, such that it's defined such that it's only non-zero over the adjacent elements to which that particular node 3 is attached. And then otherwise, let's say in elements 1 and elements 4, this particular basis function is assumed to just be equal to 0 in each of these two domains. So this is one of my funny basis functions, my finite element basis functions. And sometimes they're also referred to as hat functions because they kind of look like a party hat, one of those triangular or conic hats that you might have at somebody's birthday or something like that. So hat functions, finite element basis functions, all kind of referring to the same things. So there's some nice properties of finite element basis functions. And to revisit some of the things that we mentioned early on, one of the nice properties of finite element basis functions is that they constitute an interpolation of these nodal coefficients or the nodal values of the displacement along the length of the domain. So that's one nice property. It turns out that this interpolatory property is particularly nice for interpreting what these values actually represent. They're actually the values of the displacement field evaluated at these corresponding node locations. And actually, it makes it a lot easier to enforce boundary conditions. If I wanted to enforce the condition that my function u of x has to be equal to 0 at a particular location where I've defined a node, all I have to do is set that particular coefficient, u5 or u1, directly equal to 0 or to whatever imposed value of displacement. So enforcing boundary conditions using this particular interpolatory representation of the solution makes things a lot easier. Okay, so that's one nice property. We have this interpolation property. The other nice kind of aside, I guess you could call this a corollary or kind of a follow-on, a consequence of this interpolation property is that these basis functions actually satisfy this so-called Kronecker delta property. It's really a statement that each of my corresponding basis functions has to be equal to 1 at the location where, I'm kind of like have a particular node defined. So for basis function number 3, let's say, associated with node 3, it might be easier to kind of visualize this in this example. This particular basis function has a value of 1 at node 3, and then otherwise at all other nodal values, x1, x2, x4, x5, this basis function is equal to 0 at those locations. That's essentially what this statement of the Kronecker delta property is saying. My basis function is equal to 1 at the corresponding node that basis function is associated with, and it's equal to 0 at the other nodal locations. That's kind of, again, a consequence of this interpolatory property. But there's another interesting aside that I'll kind of point to regarding these properties in relation to how these basis functions are defined, and that is that they satisfy a so-called partition of unity. Not only are they, respectively equal to 1 at their corresponding nodes and equal to 0 at the other nodes, which implies that, all these basis functions should sum to 1 at each one of the different nodal locations. But it turns out actually that in general, they all sum to 1 at all possible values of x or coordinates x along the length of the domain. You can see that by taking a look just at the two shape functions associated with two nodes terminating a given element. If you sum those shape functions together, the minus c cancels with c and you just get 1. So n1 plus n2 is equal to 1 at all possible values of c ranging from 0 to 1. So that's the partition of unity property. That actually kind of ensures a few other nice benefits of finite element basis functions, but those are kind of like in the details, so we won't kind of belabor that, but that's kind of a good thing to know, that all the basis functions should sum to 1. And the final property that actually is kind of, well, arguably one of the biggest powers, besides the fact that, the interpolatory property makes it easy to enforce boundary conditions at these discrete nodal locations. The other thing that makes finite element basis functions really appealing is the so-called compact support property. That's the property that says that these basis functions are really only non-zero over the collection of elements to which a given node is attached. So basis function 3 is only non-zero in these two elements that are attached to node 3, and elsewhere it's equal to 0. And we'll see actually that this property results in a form for the stiffness matrix that has a nice sparse and banded structure. And that makes it a lot easier to set up and solve systems of equations which don't result in a dense stiffness matrix. If you have a lot of zeros, in other words, or a sparse matrix, for your stiffness matrix, that turns out to require less computational effort to invert and solve. So a lot of nice properties of finite element basis functions that derive from choosing this particular interpolatory form. So in the next lecture, we're going to talk about how we actually apply these finite element basis functions in the context of solving or setting up and solving these boundary value problems. So stay tuned. We'll continue some of the discussion of those details in the next lecture. But if you have questions, feel free to reach out. Otherwise, I'll see you then. All right, take it easy.